Okay. Yep. Now the third speaker, Doug Kirkpatrick. Now floor is yours.
All right,
Please go
thank you
ahead.
so much. Um, hello and good day, I should say. I shouldn't assume everyone's in my time zone. It's good morning for me. My name is Doug Kirkpatrick. I'm a PhD graduand at Michigan State University. I'm just finishing things up before I start a postdoc in a couple of weeks. I'll be talking today about some work that I did with one of my advisors, Arend Hintze, who is currently a professor at Dalarna University in Sweden. And so without any further ado, let me get into this. So this all stems from a basic question of how do we get to from where we are in terms of intelligent systems, intelligent computers, intelligent artificial intelligence to where we would want to be, to that high level generalizable artificial intelligence that's really much more useful, much more powerful in the real world. Because right now what we have are simple systems that can perhaps understand a very specific task that they're programmed for, um, but more broadly are unable to have a deeper understanding of what's actually going around it. A Roomba, for example, will not see um, my keys under the sofa and tell me that they're there. It'll simply just vacuum right around them and go on its merry way. And so what we are looking for then is something with a little bit more intelligence, a little bit more understanding, something that can realize what's going on in its environment and have a mental model of what's going on in its environment and sort of figure out how to use that in a productive manner. So in another word, we're looking for what psychologists and philosophers have referred to as mental representation. Or a mental model, something that the mind has constructed and knows about its world. Another way of looking at this is, say, were I to look out my window right here and see this, I'd think, oh, it's a great day, I'll go for a long hike. Well, if I have a mental model of what's actually going on, um, that might not be the best plan. And so you want to integrate this information and use it in a very productive way, perhaps to make that correct decision to say, bring a umbrella to do something that makes a little bit more sense. And so the question then becomes, we know that there's these mental representations out there, these mental models out there. We have them and we use them every day. But how can we figure out where they are? How can we measure them? How can we quantify them in a more meaningful sense? Because we're pretty sure that they're actually there. And so it's a question then of how do we measure this? And hopefully by some of the language that I've been putting down, you might have a quick guess that it is in fact information theory. So there's, to visualize this, we'll look at an information theoretic Venn diagram. Each of these circles is a source of noise, a source of information. And so information can come from different places. It can come from the environment, changing weather, changing structures or changing behaviors of other agents, perhaps. There can be information in our memory. There's stuff that we've learned that we've integrated. And then also importantly, there's stuff that's coming from our sensors, from what we've seen and what's coming in directly to us. And so in order to sort of quantify what we're looking for something that's in our mental model that's reflective of some greater state of the environment around us. But in order for it to be a meaningful mental model, something that we're actually understanding and using, it needs to be something that's not coming from the sensors. And so there's this information theoretic quantity, R, the measure of representations, that was sort of developed a couple of years back, and is what most of this work is based upon. And so mathematically speaking, there's a formulation for calculating it using Shannon entropies. We run the systems through a bunch of different world states and do a pseudo count to generate the probabilities of each state and then use those probabilities to calculate the respective entropies. And so just as a quick summary, what does R actually mean? R measures how much the agent knows about its environment without consulting its sensors. The downside, as it were, to R is that it doesn't really describe how the internal model is used, how the internal model is structured. And so to that end, a couple of, I think it was 3 A-Lifes ago, myself, Chris Adami, one of my other advisors, and Arend published a paper that described another metric referred to as the smearedness of representations. And so it's more of a measurement of where the representations are and how they're distributed throughout the network. If they're more concentrated, if information about specific concepts in the environment are concentrated in specific nodes of the brain, or if those are all more widely distributed. And so mathematically speaking, smearedness is calculated as a pairwise minimum of all these things. When you have, you can calculate an atomic R for the information about a specific concept in a specific node of the brain, do that for all of them, and you get this whole matrix of information where things are located in the brain. If you saw Cliff Boehm's talk yesterday, he presented some an interesting continuation where we further look into where specific concepts are stored and use that to build a network map of how these agents are actually using the information. But unfortunately, we didn't get a chance to integrate with that with the work done here yet. So then the question is, how do we sort of evolve these representations? What makes this an evolutionary process, something that's useful for the A-Life community? And while we have these Markov brains, they're basically sparse neural networks with highly composable and different computational components that are called the gates. Those are those middle units that you see there. There's also input and output neurons that sort of read information from and write information to the environment that allow it to interact with the environment. And there's also these recurrent or hidden nodes that are the memory of the Markov brain that allow it to actually store and propagate information over time. And so evolutionary speaking, we encode each of these gates and the connections between the gates into a genome that has different start codons that code for different types of gates. And so with that, we can sort of, we have our genomes, so we can evaluate them on a task. Here we use the active categorical perception task or the block catch task because the some blocks are dropped towards the agents, either small or large, and the agent must either I think it's catch the small blocks and avoid the large blocks. We do both variations in different contexts. And just to sort of help you visualize that, here's a quick video. So the agents see this information over time, and because of the gap in the middle of their sensors, they have to actively integrate the information in order to make the correct decision because they can't see the whole block at any one time, or they can't be sure that they're seeing the whole block at any one point in time. And so we run them through a number of different conditions, a small subset of which are shown here, and we evaluate them. Do they correctly catch the block, or do they incorrectly avoid the block, or vice versa, depending on the size of the block that's given? And so we use this in the original work. This was used to calculate a basic sort of fitness function, an exponential to sort of help stratify out things as you got to the higher levels of performance. And so this works. If you evolve agents and Markov brains or even different network types over time, you will eventually get meaningful performance. You'll get something like, say, 90%, I believe, is the default for Markov brains. But the interesting thing here is, since we have access to those recurrent nodes, to those hidden nodes, we can figure out what's going on in there. We can see, okay, do they understand using that information theoretic measure if the block is moving to the left or to the right? And we can calculate the R value of how much understanding they have in total for a number of different concepts there. And so another piece of previous work that I've really built off of, done by Jory Shasau, would be this idea of R augmentation, where in addition to optimizing for task performance, you also add in this additional term that allows you to optimize for understanding, for how much representation they're actually measuring. And so this sort of setup is built to maximize their understanding. It's basically optimizes for a maximum value of R, for that maximum value of understanding. But there was one sort of nagging question. Is this sort of raw maximization the best way to do it? Especially with these new metrics that we're coming out with in terms of smearedness and the thing that Cliff talked about, fragmentation. There's different targets that we can optimize for. And so the whole point of this investigation was to sort of say, okay, how can we look at different ways to optimize on these different axes toward these different metrics? And so there's, you can do augment for max distribution, for max smearedness. Or you can do the inverse, mathematically speaking, and set it up so that it moves towards the smallest possible smearedness, so that the states are very discrete. However, neither of these is really ideal. They don't really, you need some sort of intermediary level. And so we tested this. We tested the control, the R maximization, and the S max and the S min. And as was sort of expected, the R maximization was really the best option. It outperformed all of the others, both in terms of final performance and performance over evolutionary time. And so that sort of says that there might be something still there, because we're still getting pretty decent performance when we're optimizing with the smearedness. So what if we say augment towards a sort of Goldilocks value, somewhere in the middle, because that might provide a more useful structure for the network to optimize around. And so we basically started just by trying a different range of target values. So we optimized towards a bunch of different target values, and that should be 2, 4, 6, 8, 10. That edit did not make it through to the final presentation, so I apologize. But there's actually, we tested it on just a range of 5 values. Some of them did actually outperform our augmentation, at least to a slight degree. But really at this point, we were just throwing darts at a dartboard. And so to have a more effective way of looking at, okay, what might the actual ideal target value be instead of just throwing these around, we decided to look at map elites. For those that are not familiar, map elites is a diversification optimizer in that it maintains a grid of these different with these different values on different axes that allow you to sort of stratify out and look at solutions that have different values. So in our case, we're looking at systems that have different values of R or different values of S, and maintain these different sort of networks that have these different structural properties, and sort of see where the best value lies. The original intent was just to use this as a way of setting up the target value, but when we were looking at it, we found something interesting. The first thing was that it seems like there might actually be an intermediate value for R itself that isn't in fact ideal. So R maximization might not even be the best option. 2, there definitely is an intermediate value for smearedness that would be optimal as well. But then there was one final thing that was also really interesting, which was that when we were running both the map elites and the typical roulette selection evolution for the same amount of time, the map elites actually outperformed the roulette selection for that same for the same number of agent evaluations. So just to summarize, we can measure these mental representations and where they are distributed. Minimizing or maximizing that distribution, that smearedness, does not increase performance. Optimizing towards that target value, that intermediate value, may be very useful. However, it's hard to tell what that target value is going to be for any given task. And then with some further work necessary to explore the possible ramifications, map elites provide a different powerful way to optimize both representations and their structure. And so there's a lot of opportunity here in terms of shaping the structure and direction of neural networks and how they can be formed. And so that's something that I definitely want to look into in the future. So just some quick thanks to my fiance and our beloved pets, who unfortunately are not making an appearance today. And then to all my coworkers, my advisors, Arend and Chris, and everyone else that I've worked with at MSU. Yeah, that's running low on time. So I will open up the floor to questions.
Thank you very much, Doug. So perfect timing. So we can take several questions. So now it's open to question. Audience, please feel free to unmute and ask questions. Or you can type your question to the chat.
I do have a question. So first off, thanks very much for the talk. I really enjoyed it. I'm unfamiliar with this R term, and I'm curious, how much better is it to use R than to naively use the mutual information of the network state and this value we're trying to predict?
So I don't know that off the top of my head. I know that the construction of the R term in particular was to make sure that you're actually was structured to mimic the philosophical cognitive science literature, where you've got this information that's actually usefully stored. Maybe Arend or Chris, who I think are both on here, can chime in and correct me if I'm wrong, but I don't know that that direct comparison has been done, or at least I don't remember having been done off the top of my head.
I think just to add this, we did try using direct mutual information without sensor information, and it actually also works, but sort of you're missing, when you're doing this, you're missing the amount of information that is actually held by the brain or sort of as an internal state, as opposed to just using mutual information. So if you want to optimize a artificial neural network that is not recurrent, what you suggested will work perfectly fine. However, if you want to optimize a recurrent neural network, then doing this R measure, I think, is better.
Okay. We can take more questions. I have one. So Doug, could you give us some explanation of the relationship between this smearedness measurement and human interpretability? For example, if that's the high S value, does it mean that it's actually easier for us to understand how and where the representation is located?
Sure. I would argue that it's actually the opposite.
Opposite, sorry about
that. High smearedness means it's highly distributed. Each concept is contained in multiple nodes across the network. And so low smearedness means that each of those concepts is stored in perhaps one or two nodes across the network, which at least for human interpretability would make it easier to focus in on a specific location as containing useful information. And this is something that we've been refining further. And there was the talk yesterday by Clifford Bohm talking about some of our other work with fragmentation, which is an extension of sort of this whole R and smearedness, with looking at the specific nodes and which set of nodes contain useful information, which would definitely be something that would be highly powerful in working on interpretability.
Yeah,
thank you.
But your chart shows that the low smearedness actually is negatively affecting the performance, right? So we shouldn't really aim at the perfect interpretability if we want to achieve,
well, at a certain point, you need to have some interaction between the different nodes, between the different concepts in order to make a decision. You have to know that it is both moving to the left and a small block in order to know which way to move. And so at some point that's why you need that Goldilocks level to sort of figure out where there's actually enough information interaction for computation to happen, as opposed to just having everything siloed and it can't interact and you can't make a useful decision.
Yep, that makes sense. All right. So any additional quick questions? Okay, so let's move on. So thank you very much, Doug.
Thank you.